Hi, my name is Sharrock. I'm just starting out as a Ph.D. student at Imperial College London. And just first off, a thank you to Stephen and the BayesiaLab team for having me. So as you've briefly introduced, I'm going to be talking about an application of Bayesian networks to yield prediction in Portuguese viticulture. So just a brief overview of the talk. Just going to start with a brief introduction to some of the background, some of the context for this project, then very brief run through of Bayesian networks. Then I'll look at some of the current state-of-the-art techniques, what is used at the moment in terms of statistical models for modeling yield prediction in viticulture. Then look at our own model development, and finally some conclusions. So like I say, I'll start with some of the introduction. As with many Bayesian networks, it's kind of crucial to have some kind of background knowledge of the domain that we're interested in before we start modeling. And I know certainly from my own personal experience, being a keen wine drinker didn't necessarily translate to kind of any knowledge of viticulture or how wine grapes are grown or anything like that. So with that in mind, let's just jump to, let me make sure we can see everything. So a bit better. So this slide just shows the annual life cycle of the grapevine. And classically, the annual life cycle is divided into four main phenological stages. So those are bud burst, flowering, fruit set, and veraison. And of course, then harvest and the dormancy of the grapevine. Each of these different stages is important in the development of the grape berry, and each of them is characterized by a slightly different set of physiological processes. So bud burst, as the name might suggest, corresponds to the formation of small buds on the vine and then the burst of these. This typically in the northern hemisphere happens around February or March, when average temperatures consistently reach around 10 degrees Celsius. This is followed by flowering. Again, fairly obvious from the name what this is. Formation of small flowers on the grapevine itself. This is generally about 40 to 80 days after the bud burst, and typically occurs in around May when temperatures are between 15 and 20 degrees Celsius. We move on to fruit set. This essentially refers to when pollination and fertilization occur. Successfully pollinated ovules will develop into seeds, which then grow into fruit berries, and this stage is particularly important for determining final grapevine yields, as, of course, it determines the maximum yield that we could possibly have. The final stage, veraison, is a French term which essentially roughly corresponds to the change of color of berries or the maturation of the berries. And this kind of concludes the growing season. They're then harvested and then go into dormancy before the next season. So as we've kind of alluded to already, each of these stages are affected by a myriad of different kind of climate influences, and these are kind of summarized very, very briefly on the board. Temperature, precipitation, wind, extreme weather, all of these different things interact with the way the grape berries form in a fairly complex way. It's also very specific to different grapevine varieties, and this was something we thought we might be able to capture in a Bayesian network. So these kind of interactions are relatively well understood. The physiological processes leading to grapevine formation are relatively well understood. However, this hasn't translated to a particularly accurate or robust method for yield prediction, which is of great interest for farmers and viticulturists who are interested in having some kind of idea of what they might expect from their yield from year to year early in the growing season. So traditionally, yield prediction is based on the following formula, fairly simplistic. Predicted yield is given as a product of the number of vines per acre, the number of clusters per vine, and the predicted cluster weight, and then normalized by this factor of 2000. And of course, the variability in this equation stems from the predicted cluster weight. Again, traditionally, there are a number of methods which people have used to estimate the predicted cluster weight. These range from the harvest cluster weight method, which uses kind of historical averages to estimate what the cluster weight may be for the season that we're interested in. Of course, this is flawed simply from the fact that year to year there may be a great interannual variability. The The lag phase method and the growing degree day method, these both assume some kind of linear relationship between the weight of clusters at a certain point earlier in that growing season and the final cluster weight. Of course, these two methods, again, are flawed by the fact they don't really take into account any of the bioclimatic variables which we have seen are fairly crucial for influencing yield formation. So this kind of led us to this objective for this work, and that was to develop a Bayesian network model which could estimate total grapevine yield at several stages during the growing season, in order mainly to provide an accurate prediction of good and bad production years, but also to assess the relative importance of various factors known to influence yields, and to evaluate the potential impact of climate change projections on wine production. So with that, on to kind of the mathematical tool, Bayesian networks. I'm going to kind of skip these two slides. I'm sure all of you know more about Bayesian networks than I do. So I'm going to move on to this, which is kind of a general flowchart of how I went about kind of building this model, and I think this is a fairly standard way of doing so. Firstly, to define the modeling purpose and the context, and that's kind of what we talked about already in the introduction. Then on to defining relevant variables or variable selection, learning the network structure, learning the network parameters, validating the network, i.e. checking how well it works with respect to some kind of independent data set, and finally evaluating the network. Does it work as we might expect from what we know already about these processes? And ideally, this is an iterative process. Of course, what we learn from our network evaluation feeds back into the model, and then we can refine and develop later on. So what led us to kind of using the Bayesian network for this purpose? Well, the main one for me personally was the fact that it allows for use by non-experts due to kind of the qualitative component or the graphical construction. For this to be used by people in the field, by farmers, by viticulturalists, it had to have some kind of form that would be readily understandable by a non-expert. And I think the qualitative component, the directed acyclic graph component of the Bayesian network means that it is a suitable tool for that purpose. Also, and particularly of interest, was that, as we've heard already, it can be readily integrated into a decision support system, i.e. we could feed this model into some kind of network with decision nodes, utility nodes, such that farmers could make decisions early on in the growing season which would have a realizable benefit later on in that season. Several limitations, however, which I want to note at this point. Firstly, domain uncertainty. There are aspects of this domain which we couldn't necessarily incorporate into our model, and these may have had some significant impact on the final grapevine yield. And also, and I'm going to talk about this in more depth later, the need for discretization. Of course, there are continuous Bayesian network models, but simply due to computational demands, we just considered the discrete case here. So that's the Bayesian network. What are the current state-of-the-art tools being used at the moment in the industry for yield prediction? In statistical terms, well, in the Portuguese viticultural setting, which is what I'm going to restrict attention to, that's the data set we were looking at. There are two main classes of models. The first are statistical models, and these generally take the form of fairly simplistic kind of autoregressive models, or otherwise linear or multinomial logistic regression models, which essentially take grapevine yield or wine production as a proxy, as the dependent variable, and regress that against this set of bioclimatic parameters which we've already talked about. There are a number of examples of this with varying success, and each of these studies tends to identify different climatic factors being significant. One of these recent studies we're going to use as kind of a benchmark, and this one by Santos et al. In 2013, they achieved a classification rate on a kind of cross-validated basis of around 70%, and we see that as kind of a reasonable benchmark against which to test the performance of our own model. The second type of model, dynamic models, these are kind of numerical simulation-based models, and these are much less common, and that's largely due to the fact that these are very computationally intensive. So, is there any evidence that the Bayesian network might prove fruitful in this setting? Well, yes. There have been examples of the use of Bayesian networks for yield prediction in other settings. So, for a whole range of crops, ranging from wheat to rapeseed to rice crops, there's been numerous examples. So I'm not going to go into a huge amount of detail on these different examples in particular. What I will pick out is a trend in these studies for a movement from defining network structure on the basis of expert knowledge or pre-existing mathematical models in the early examples to more recent examples which have tended to learn network structure on a more data-driven basis. I guess with kind of the growing popularity of techniques, machine learning techniques, that kind of thing, that's something we've seen across a wide different areas of statistics and mathematics. Again, I emphasize the fact that no previous studies have actually looked at applying this kind of tool in the viticultural context. So on to our own model development, and again I'll phrase this in terms of the flowchart, which I brought up earlier. So firstly, defining modeling purpose and context, and largely talked about that already, but it was also shaped by the data we had available. Originally, we were hoping to receive a relatively long time series of data from the Portuguese government. That eventually fell through, and so we used some publicly accessible data, which essentially consists of a time series of wine production, which we're going to use as a proxy for grapevine yield in the Douro demarcated region, which is kind of the top right, it's the dark green area. And then for our independent variables or kind of evidence nodes, we had a time series of climatic variables from a meteorological station at a particular place within that region. We also, due to the relatively short time series we had available, and therefore the small number of observations, we also considered a second data set, which consisted of concatenating several different time series from different municipalities within this region. However, the results we got from this weren't particularly encouraging, and although it does need further work to understand this properly, we think that's down to the fact that individual cultivars and individual varieties of grape have highly specific relationships to climatic variables, and therefore it's quite hard to fit one model to a large number of different regions at once. So on to the next stage of the model development, and that's defining relevant variables. We took kind of two approaches here. The first, knowledge-based, we looked at variables which had previously been identified as significant for studies within this region, and they're kind of summarized in this table at the top. So we have total precipitation from various months, we have the average temperature from various months, and we have some other variables, namely the minimum temperature in May and the maximum temperature in June. The second approach we took was data-based, and I think this is another area where there's room for more work. As we've heard already, BayesiaLab seems to provide a large number of tools for kind of variable selection within the program itself. Unfortunately, this I was coding up in R mainly, and so I kind of restricted my attention to this elastic net penalized regression approach for selecting variables for the data. This approach is quite suitable when you have a large number of covariates, much larger than the number of observations. What we have essentially here at the bottom is it consists of, the first term is essentially the coefficients you'd get from a simple least squares regression approach. The second term is this regularization term, which hopefully prevents you from overfitting. So lambda is kind of some kind of parameter which controls the extent of regularization, and alpha is a mixing term which hopefully encourages you to include groups of highly correlated variables. So you don't simply pick out one variable and leave out the rest of the variables which may be correlated to that variable, and obviously that's something that Bayesian network can take advantage of. So on to learning the network structure. Again, we took two approaches here. Knowledge-based, i.e. I as the modeler defined some kind of network structure which may seem relevant or reasonable. And then a data-based approach. Again, this is another area where we could look at different approaches and different methods to learning the network structure. In particular here, I used a Bayesian search and score method, and I know several recent papers have suggested that kind of an information theoretic approach might yield better results. So this is, again, something we can look at. But the scoring function I chose here was a BDE function, which is essentially represents the posterior probability of the network given the data under certain assumptions on our prior. And again, the search algorithm was greedy hill climbing. So the network parameters, I'll kind of skip over this. We estimated them standard approach using the MOP estimates, and in the case of latent variables, using the EM algorithm. So what do we end up with? Well, we end up with a set of different alpha level models or prototype networks. The first 6 of these, we defined both the structure and the set of variables to include. The 7th and the 8th, we define the variables to include, but the network structure is learned from the data. And the final 2 models, both the set of variables and the network structure, are both learnt. So how do we assess which of these models to go forward with? That's network validation, and we assess the performance of each of these models on the basis of a simple, simplistic leave one out cross-validation scheme. And on that basis, we determined that the 7th and the 8th models were those which we should prefer. And the crucial result here is that the classification rate is fairly favorable compared to existing models out there. So we achieved around an 80% classification rate, again using this leave one out cross-validation scheme, which is fairly encouraging. Again, there's not much difference between this and the 9th and the 10th models, which we remember were those which we learned from the data, both the variables and the network structure. In this case, we tended to favour the networks where we'd actually defined the variables, simply because it seemed like that would help us to avoid overfitting if this model were to be generalised to another data set. So, on the basis of that analysis, we arrive at this model, the 3-state model shown on the left. I haven't really talked about discretization. It was observed, however, that the models we learned from the data were fairly dependent on the discretization scheme we used. Again, here's another area where we could look at improving things further. And so, on that basis, I'm just going to I've included the results for a 2-state model as well, where each of the states was discretized into 2 rather than 3 states. So finally, this process concludes with a network evaluation. How well does the network perform? Does it perform, or does it respond as we might expect, given our knowledge of the way different climatic variables interact with the yield formation process? So we first looked at some kind of evidence sensitivity analysis, which essentially asked the question, how sensitive is the posterior distribution of the query node, i.e. wine production in this case, or yield formation, to variations in the set of evidence? The results here are interesting and in some sense surprising, and again, they do highlight the sensitivity of the model we've come up with to discretization. In particular, the variable which was identified as being sharing the most mutual information in the 2-state model, that is the average temperature in February, was actually excluded entirely when we learnt the network in the 3-state model. Again, that's something which perhaps could do with further information. However, in terms of other variables, the average temperature in the average precipitation in May, the maximum temperature in June, both of the models seem to pick these up as highly significant. And this actually corresponds quite well to previous studies. Not one, but a number of previous studies have actually picked up both of these variables as being significant. As a secondary analysis, we looked at a parameter sensitivity analysis, and the question is, how sensitive is the query node, again, wine production, to variations in the values of the model parameters? Just for the sake of time, I'm just going to focus on a couple of these here. What we're looking at here is the posterior probability of the highest state of production along the x-axis, and what we can see is, firstly, looking at the top bar, as the prior probability of the average temperature in February being in its lowest state, i.e. not having a high average temperature in February, increases, we see that the probability of a good production year also increases. Similarly, looking at the second bar down, we see that as the prior probability of the average temperature in June being in its lowest state, i.e. having a low average temperature in June, as that decreases, now see that the posterior probability of a good production year increases. Both of these observations, again, correspond quite well to what we've seen observed in the literature already. And finally, simulations and what-if scenarios. And this, again, is one of the great things about Bayesian networks. We can kind of graphically represent different known scenarios and ask what happens when we simulate various things. What we have at the top is a simulation of warm and dry conditions during the 2 stages of flowering and veraison. And what we see in that case is reflected in the posterior probabilities for a good or bad production year. And we see that we have a high posterior probability of a high or a good year for production. And again, that's something which we know is likely to happen from the physiological side of things. The opposite scenario in the bottom, when we specify cool and wet conditions during flowering veraison, we end up with the opposite conclusion, as we should expect. To conclude, one final question we might ask is, how does the model perform in the absence of a complete set of evidence? And this is particularly important in this setting. The question essentially is, does the model do so well early on in the growing season when we might be particularly interested in classifying whether that year is going to be a good or bad production year? And the results are relatively encouraging for the 2-state model, again, perhaps suggesting a preference for that model. In particular, we see that by February, we're already obtaining a relatively good classification rate, and this only improves as the year goes on and we move towards harvest. So to conclude, we've relatively successfully developed a prototype, and it is a prototype Bayesian network model to predict total grapevine yield at several stages of the growing season. Demonstrated that this model can successfully classify good and bad production years, used the model to assess the relative importance of various factors known to influence grapevine yield, and verified that this model does what we expect it to, using known physiological scenarios and against existing statistical models. There is a fair amount of further work required. As we've talked about, there are various limitations and shortcomings of the current model. We would like to assess whether this model does generalize to further independent data sets. And finally, it would be quite interesting to fully integrate this model into a Bayesian decision network. Thank you, and I'd love to hear any questions.